Well, welcome back to our course on systems design as we're looking at systems and analysis from the point of view of Dennis, Wixom, and Roth, with a primary focus from this textbook being on an information system development. And we're now in the last lecture in the design phase. And so we've covered various aspects of what we would need for an effective information system. And the last part is looking at the data storage design. So let's get into this material. And another important activity of the design phase is to design the data storage component of the system. So what we're covering in this lecture and this chapter describes the activities that are performed when first developing the data storage design. So the first step is we want to consider the different ways in which data can be stored and described. Several important characteristics that should be considered when selecting the data storage format are discussed. The process of revising the logical data model into the physical data model is then outlined because one of the most popular data formats today is a relational database. Optimization of relational databases from both storage and access perspectives are also something that we'll talk about. So the objectives, we want to become familiar with several file and database formats. We'll go through them one at a time. We'll describe several goals of the data storage. We'll be able to revise a logical ERD to physical ERD, and we'll explain what that is. We'll be able to optimize a relational database for data storage and data access. We'll also want to get familiar with indexing. And finally, we'll be able to estimate the size of a database. So what do we do with databases and data storage? And so let's have an introduction for that. The data storage function is how the data is stored and handled by programmers that run the system. In terms of the data storage design, we want to select the data storage format. We want to convert the logical data models into a physical data model to reflect the implementation decisions. We want to ensure that the DFDs and the ERDs balance, and then design the selected data storage format to optimize its processing efficiently. So in terms of the formats, there's two main types of data storage formats. First would be files, where you have an electronic list of data optimized to perform a particular transaction. And the other is a database. It's a collection of groupings of information that are related to each other in some way. We have the database management system, DBMS, the software. We want to be thinking about the software that creates and manipulates these databases. So for files, the data files are represent an electronic list of information that is formatted for a particular transaction. The sequential organization is common. The record associations with other records are created by pointers, and it's also called linked lists because of the way that the records are linked together using pointers. So here are the various types of files that we can be dealing with. The master files, it stores the core information that's important to the application. Lookup files, these contain static values. Transactions files of these store the information that can be used to update a master file. Audit files are records, quote, before and, quote, after images of the data as the data is altered. Finally, we have history files or archiving files that store past transactions. So here is just an example from the textbook that shows the appointment files. And you can see there's appointment date, time, duration, reason, patient, the first and last name of the patient, their phone number, the doctor ID, and the doctor's last name. So this would be a way of how we're looking how a doctor, how long he's spending with the patient, what is the reason, and relating the patient to the doctor and the time and date. So here are the 5 types of databases that we'll discuss: the legacy database, relational database, object database, multi-dimensional database, and a NoSQL database. And we'll have charts on each one of these, and so I'll just have that listing to start out with and then get into the details. For legacy databases, databases which are based on older technology, and these are seldom used to develop new applications, but you may have a legacy database that you have to refer to. And so there's 2 major types, hierarchical databases. And these use hierarchies or inverted trees to represent relationships. And there's also network databases that are collections of records that are related to each other through pointers. Next, we have relational databases, and these are the most popular kind of database for application development today. It's based on a collection of tables, each of which has a primary key. The tables are related to each other by placing the primary key from one table into the related table as a foreign key. Most relational database management system, RDBMS, support referential integrity, and they ensure that the values linking the tables together are valid and correctly synchronized. There's also the structured SQL language, SQL, and this is the standard language for accessing the data in the tables. So here we can see an appointment database, and so we're having these various tables related to one another. And so this just gives you an idea, trying to, in a picture form, to give you a sense of what we are doing with a relational database. So I refer you to the textbook to thinking about that in more detail. Next, we have object databases, and they're based on object orientation. All things should be treated as objects, having both data, that is attributes, and processes, which are behaviors. An object-oriented database management system, ODBMS, are mainly used to support multimedia applications or systems that involve complex data. They end up playing a minor role in the database management system market currently. You can also have multi-dimensional databases. It's a type of relational database used extensively in data warehousing. Data warehousing is a practice of taking and storing data in a data warehouse that is a large database that supports business intelligence or BI systems. Data marts are small bases based on data warehouses data, support BI, and they support BI for specific departments or functional areas of an organization. They store data to support aggregations of data on multiple dimensions. When the data are first loaded into a multi-dimensional database, the database pre-calculates the data across the multiple dimensions and stores the answers for fast access. And so here's just an illustration of what a multi-dimensional database could look like. And so you have the order date, so you have a temporal value, you have a customer listing, and then you have a payment type. There could be many types of ways that you could have multi-dimensional information, but that's just an example of relating 3 there. Finally, we have a NoSQL database. It's the newest database approach. It's not based on the relational model or SQL. It gets into rapid processing on replicated database servers in the cloud. So this is where we would see this in cloud-oriented type of things. And there's various types that are included. You can have a document-oriented database, and so they manage the collection of documents of various forms and structures. MongoDB, which may be something that you have utilized, say for mobile apps, could be an example there. You could also have wide column databases. They store data in records holding very large numbers of dynamic columns, which could be potentially billions. And examples are Bigtable, Cassandra, and Dynamo. And you also could have a graph database, which is a collection of nodes and edges using graph theory to store, map, and query relationships. And so if you haven't been exposed to graph theory, I have two courses that you may want to look over. First is discrete mathematics, and the other is data structures, and it comes up in both of those courses. So in terms of selecting a storage format, each of the file and database data storage formats has its strengths and its weaknesses. Factors to consider in selecting a storage format are the data types you'll be utilizing, the type of application systems that will be considered, the existing storage formats that have been created, and what would be the future needs. Okay, so here is an example of data storage formats. And so we have legacy, relational, object, database, multidimensional, NoSQL, and also files. I'm not going to go through all of the details in this table, but you can pause the video or look at the textbook. But we can be considering the major strengths and major weaknesses, the data type supported, the application system type supported, existing data formats, and future needs. So, and then this can help give you some perspective of like, well, what should you be utilizing, or at least what you should you be considering before you go and do an analysis of alternatives and make that final determination. Okay, let's look at moving from a logical to a physical data model. So the logical entity relational diagram, ERD, so we talked about the objectives, we talked about ERDs, and so that's what it stands for. It depicts the business view of the data, and it omits the implementation detail, just like the DRDs. We're just trying to give the higher level perspective. Having determined the data storage format, the physical data models are created to show the implementation details and to explain more about how the final system. So the physical ERDs, entity relationship diagrams, so that the physical ERDs include entities, relationships, and attributes. It adds references to how the data will be stored. And there is much more metadata that is defined. And metadata, if you might recall, is data about data. So here are the steps to create a physical ERD. First, we change the entity tables, the entities to tables or files. 2, we change the attributes to fields. 3, we add primary keys. 4, we add foreign keys. And 5, we add system-related components. So here is an example of a physical ERD. And so this goes back to our drone tech example. And so you could be thinking about what we've developed so far with our DRDs. And now we're going from a logical to a physical ERD. And you can see some commonalities, but we're getting some specific values that we want to be making sure we manage in our database system. Here is the physical aspects of the data element and metadata. And so having a GUI for a way of cataloging information can be quite useful. And so this is one of the ways that you can get some insight into that. Here we can be seeing various kind of database options that we can be using. Here we're highlighting Oracle. But that's not necessarily the only one that you could use. And but anyway, that's just something that you can keep in mind. Okay, we talked about CRUD matrices before. And so now we're considering what we're going to be doing for databases. We're going to be revisiting this. And so it's important to verify that the system's data flow diagrams and ERD models are balanced. So in design, logical models are converted into physical models. We want to consider the changes in the form of new processes, new data stores, and new data elements that may occur. And as a result, the CRUD matrix should be revised. So how do we think about the optimization of the data storage? The data storage format is now optimized for processing efficiency. We want to make sure that when we use the database, we get our data quickly, and we have to be considering that the nature of the data that we're going to be passing a lot. So there's two primary dimensions, the storage efficiency and the speed of the access. We want to consider limiting data redundancy, so there are very few null values within our collection of data, and we want to consider the best way to achieve efficiency, and when we look at normalization. So, okay, for access speed optimizing, after optimizing for data storage efficiency, the data are spread out across many tables. For a large relational database, it is necessary to optimize access speed. Techniques of optimizing access speed are denormalization, clustering, indexing, estimating the size of the data for hardware planning. Okay, so we have talked about normalization before. So what would be denormalization? We're adding redundancy back into the design. So we're trying to make things faster. So redundancy may help, although it may seem a little bit counterintuitive. So we reduce the number of joins required during the processing to enhance data access speed. So whatever you want to think of it, buffering or stuff like that, having cache so that we can make things run faster is what we're thinking about when we're looking at denormalization. So what are the reasons for denormalization? Number one, to the lookup table, we include the code's description of the table. Using that code if the description is often used. For one-to-one relationships, combine the tables if they're related one-to-one, if they usually are accessed together. That's going to help us with increasing the speed. For one-to-n relationships, we place the fields from the parent table to the child table if the parent fields are used frequently with child information. So once again, we're getting into caching, if you will. And finally, the star schema design. Data marts often are modeled with star schema designs, which uses denormalization to maximize the business intelligent query performance. Okay, for clustering, this gets into placing records together physically so that like records are stored close together. And so we can be thinking about intra-file clustering, where similar records in the table are stored together. And then we can have inter-file clustering that combine records from one or from more than one table that typically are retrieved together. So the more you know about the nature of how this database is going to be utilized, that's going to help you to trying to do some optimization. Well, what about indexing? A data storage index is a mini table, which is similar to an index of a book, that contains values from one or more columns in a table and the location of the value within the table. The indexes require overhead and they take up storage space, and so we have to keep that in consideration. What are some indexing guidelines? We can use indexing sparingly for transaction systems. We can use many indexes to improve response time in business intelligence systems. For each table, we can create a unique index that is based on the primary key. For each table, we can create an index that is based on the foreign key to improve the performance of joins. And we can create an index for fields that are used frequently for grouping, sorting, or criteria. What about estimating the storage size? And this gets into volumetrics. It's a technique of estimating the amount of data that the hardware must support. And there's three steps. First, we calculate the amount of raw data, all of the data stored within the database tables, that is. Two, we calculate the overhead requirement based on the database management system's vendors' recommendations. And 3, we record the number of initial records loaded into the table, as well as the expected growth per month. Here are some example. Here's a sample of volumetrics calculations. And so we can be using this information to be helping us make those decisions. And I refer you to the textbook to be thinking about that in more detail. All right, well, let's have 2 slides to do a review, and then we'll talk about key terms, and then we'll be done. So we identified and described the purpose of the 5 types of files that are used to store business information. We identified and described the purpose of the 5 types of databases that are used to store business information. We discussed the considerations to be made when selecting a database storage format. We discussed the 5 steps involved in converting the logical data model to a physical data model, and we explained the modifications that may be needed to be done when updating the CRUD matrix. We explained how to optimize the data storage design for storage efficiency. We explained the several reasons to apply denormalizations in the data storage design as we're trying to make things work better and faster. We explained the purpose and types of clustering that can be applied to the data storage design. And finally, we explained the purpose of indexing when applied to the data storage design. Okay, we have some terms that we have introduced here. Database Management System, DBMS, Business Intelligence, those are ones that we've talked about. Expert systems, we didn't really go into that, but there's some other terms that you may want to review, and I recommend that you go and get back into the textbook for more details. We have the various types of databases, and so that would be something to keep in mind. And SQL, the structured query language, that is also a useful thing to keep in your memory. All right, well, that's it for this lecture. Thank you very much.